Imagine a world where the quiet chorus of birdsong could tell us the real story of our planet's health. Birds are incredible environmental barometers,
Hmm.
and their diversity is under immense pressure from industrialization, habitat loss.
Really is.
Monitoring these vital creatures is absolutely crucial for conservation and maintaining ecological balance. But how do you keep tabs on tiny, elusive, often hidden animals across vast landscapes? It's traditionally been an enormous challenging task.
It's true. And the importance of birdsong, well, it goes far beyond just its beauty.
Right.
Each species has a distinct voice, and these vocalizations are packed with ecological data. They offer insights into species identification, how populations are distributed, even migration patterns.
Okay.
And while we have things like image-based recognition methods, they often struggle. Dense foliage, bad weather.
Yeah, you can't always get a clear shot.
Exactly. That's why sound-based recognition, particularly through birdsong, is such an indispensable tool for researchers and conservationists. It gives you a clear, consistent signal that's less affected by those visual obstacles.
So if we want to truly listen to our planet, we need a better way to hear its natural signals. Our deep dive today is into a fascinating leap forward in this area, an enhanced EfficientNet for birdsong recognition.
Hmm.
The core mission here seems to be taking these powerful recognition tools out of the lab and making them practical, lightweight, and truly effective for continuous monitoring in the field, right where they're needed most.
Precisely. Many of the, let's say, cutting-edge models for birdsong recognition, while incredibly accurate, they come with a significant cost.
Right.
They often require immense computational power, have a huge number of parameters, making them pretty impractical for the kind of embedded low-power devices you'd want for long-term remote monitoring.
Makes sense.
So this research specifically aims to propose a much more lightweight, yet still highly accurate model to overcome those exact limitations,
Right.
basically bringing advanced AI to the actual habitat.
Okay, so for a long time, the approach to automatic birdsong recognition relied on what we call traditional machine learning. Could you maybe walk us through how that typically worked and, why deep learning eventually emerged as the more robust standard?
Certainly. The process usually involved two main stages. First, feature extraction,
Okay.
where raw birdsong waveforms were transformed into specific characteristic parameters. Think of it like distilling the unique fingerprint of a birdsong.
Got it.
By capturing its distinct tonal qualities, things like mel frequency, acceptural coefficients, MFCCs, or visual representations called spectrograms.
Spectrograms, right.
The second stage was classification. Here, models like random forest or support vector machines were trained on these extracted features to identify and categorize the different songs.
So you'd feed those fingerprints into the classifier.
Exactly. But while effective in their time, these traditional methods often face challenges with computational complexity, especially with large data sets. They also struggled a bit to generalize well to new, unseen variations in bird songs. And the manual process of designing these features was time-consuming, often subjective.
So the shift to deep learning must have been a significant turning point then. What made models, especially convolutional neural networks, CNNs, and recurrent neural networks, RNNs, what made them so much more effective for analyzing these complex sound patterns?
Well, the real power of deep learning is that it fundamentally bypassed those limitations. The manual feature engineering, the poor generalization.
Okay.
Instead of researchers having to manually identify the optimal features, deep learning models learn these features directly from the raw data.
So it learns what to look for.
Precisely. CNNs, for instance, they excel at processing grid-like data, which makes them ideal for analyzing spectrograms, those images of sound we mentioned.
Right.
RNNs, on the other hand, are fantastic at understanding sequences. That's crucial for the temporal nature of birdsongs, where the order of notes really matter.
That makes sense.
And we've seen rapid advancements since then. Architectures like VGGNet, DenseNet, even transformers being adapted, consistently pushing the boundaries of recognition accuracy. It truly revolutionized the field by automating the most challenging part.
That makes a lot of sense. These deep learning models are incredibly powerful, but as you mentioned, even with all their advancements, the source points out this persistent challenge. They still tend to be quite large and resource intensive, which, as you highlighted, isn't practical for field deployment. You can't exactly put a data center on every tree branch.
Exactly. And that's precisely the problem this paper sets out to solve. It leverages the EfficientNet series of models, which are already quite well known for their impressive balance of performance and computational efficiency.
Okay, vision.
And for this particular study, they focused on EfficientNet B0 as a starting point, really aiming to make it even more optimized for these practical, embedded field monitoring devices.
This is where the real innovation comes in, I think. The researchers introduced 4 clever enhancements to that EfficientNet B0 architecture, aiming for both improved accuracy and that field convenience. What was the first major breakthrough they implemented?
The first significant enhancement was integrating the ECA, or Efficient Channel Attention mechanism.
EC. Okay.
So, the original EfficientNet B0 used something called squeeze and excitation, or SE attention. While SE attention is good, it can sometimes lead to a loss of valuable information when it compresses high-dimensional features.
It kind of squishes it down too much.
Sort of, yeah. ECA cleverly bypasses this. It uses a one-dimensional convolution to capture cross-channel interactions without reducing the dimensionality. Think of it like the model learning to prioritize different ingredients in the sound recipe without losing any of them.
Ah, okay. It keeps all the detail but focuses better.
Exactly. It enhances the model's ability to express important features, but also reduces the number of parameters. Their experiment showed this change alone boosted accuracy by 0.46% and cut parameters by about 0.64 million compared to the baseline.
Wow.
It really highlights this crucial principle. Sometimes the most effective way isn't compressing, but intelligently refining context without losing detail.
So smarter attention without the bulk, it's like teaching the model to focus better while being more agile. What was their next inventive step?
The second improvement involved adjusting the convolution kernel size within the MBConv structure.
Yeah.
That's a core building block of EfficientNet.
Right.
The original EfficientNet B0 used both 3x3 and 5x5 kernels, but the researchers found that an excessively large receptive field, you can imagine like in the model's eyesight, where the larger kernel tries to see a very wide area, that can actually diminish the effectiveness of the attention mechanism.
Interesting. So bigger isn't always better there.
Apparently not in this case, so they modified the architecture, replacing all the 5x5 convolutions with smaller 3x3 ones in specific internal processing steps, the third, fifth, and sixth MBConv modules.
Okay.
This seemingly small change had a really profound impact. It reduced the total number of parameters and, remarkably, led to a notable 2.1% accuracy enhancement.
2% just from changing the kernel size?
Yeah, it really challenges that intuitive idea, showing how precision and efficiency can sometimes be found in focusing on finer details.
Reducing kernel size for better focus and efficiency, that's truly counterintuitive and fascinating. And the third enhancement they brought in?
The third key enhancement was incorporating this CBAM, or Convolutional Block Attention Module, attention mechanism.
CBAM. Okay, another attention type.
Right. They put this into several intermediate internal processing steps of the MBConv structure. Now, while ECA is great for focusing on channel-specific information, it doesn't really consider where that information is located spatially within the features.
Ah, the spatial aspect.
Exactly. CBAM, by contrast, integrates both channel attention and spatial attention. This lets the model selectively focus on the most crucial information across both the what and where dimensions of the feature maps.
So it knows what's important and where it is.
Precisely. Their experiments indicated the best performance came when CBAM was strategically placed into the first internal layer of these intermediate processing steps. This addition further improved recognition accuracy by 1.7%, with only a minimal increase in parameters.
It sounds like a really holistic approach to attention, making sure the model isn't just looking at the right features, but also the most important parts of those features. And finally, the fourth major improvement, which focused on the model's training process.
The final enhancement focused on optimizing the learning process itself, switching from the traditional SGD, or stochastic gradient descent, optimization algorithm to the ADAM, or adaptive moment estimation algorithm.
Adam, okay, I've heard of that one.
Yeah, it's quite popular now. SGD, while fundamental, can be slow to converge, and it's sometimes prone to getting stuck in local optima during training.
Right, not the best possible solution.
ADAM, on the other hand, is an adaptive algorithm. It dynamically adjusts the learning rate for each parameter. This dramatically accelerates convergence and significantly improves the model's ability to generalize to new data by normalizing parameter updates.
So it learns faster and better.
Basically, yes. Comparisons showed ADAM reduced training time by a remarkable 28% to 37%.
Wow.
And improved accuracy by anywhere from 0.22% up to an astounding 6.72% compared to SGD, depending on the learning rates used. With ADAM, the model hit that 96.04% accuracy in just 809 seconds.
That's fast.
And its error curve also converged much more rapidly into a lower error. This change makes the model not just accurate and lightweight, but also much faster to train and deploy, which is crucial for real-world applications.
With all these clever architectural tweaks, the ultimate test, of course, is how it performs when actually listening to birds in the wild. So, what does this all mean when we talk about real-world birdsong recognition? How did this enhanced model actually perform with real birdsong data?
Right, the proof is in the pudding, as they say. The model was rigorously trained and tested on two large, publicly available data sets, Birds data and Xenocanto.
Okay, standard data sets.
Yeah. Combined, they comprised over 32,000 birdsong samples from 10 distinct species. Everything was standardized into 2-second WAV files for consistency, and the experimental setup was robust, using a powerful GPU, PyTorch, ensuring the results were reliable and reproducible.
And the results. Did it truly live up to that promise of being both accurate and lightweight for those vital field applications?
It absolutely did. The proposed enhanced EfficientNet model achieved an impressive 96.04% accuracy in recognizing these 10 bird species.
96%. That's high.
It is. And this represents a significant 3.2% improvement over the original EfficientNet B0 model. But what's particularly compelling is that it also managed to reduce the parameter count by 16.4% compared to the original.
16% fewer parameters.
Yes, making it genuinely lightweight and convenient for deployment on field devices. This directly addresses that goal of creating a model that can run efficiently on devices with limited power and processing, extending battery life, reducing hardware costs.
It's remarkable. Genuinely better performance with less computational demand. So how does it stack up against other state-of-the-art lightweight deep learning models out there?
Well, they did direct comparisons against other popular lightweight models like MobileNet V2, MobileNet V3, EfficientNet B2, GhostNet B2, and ShuffleNet. Our model consistently demonstrated superior performance across the board.
Really?
Across all of them.
Pretty much. For instance, it was 1.43% more accurate than MobileNet V2 while using 4% fewer parameters.
Okay.
And crucially, it achieved a 1.42% accuracy improvement over the official EfficientNet V2 while reducing parameters by a staggering 84%. 84%. Compared to EfficientNet V2.
84%.
Oh.
That reduction is a massive game changer for field deployment. It translates directly to lower memory needs, faster inference times, significantly less power consumption.
So you could run it on much simpler, cheaper hardware.
Exactly. Across most weighted evaluation scenarios, it ranked highest in performance, showing its adaptability where both accuracy and efficiency are critical. The accuracy curves they showed really told the story. Our model pulls ahead of the others by about the 15th training iteration and just stays there.
That's a really compelling case for its efficiency. I'm curious, though, were there any specific species that proved particularly challenging for the model, even with all these enhancements?
Yes, and that's an important point. A detailed analysis of the confusion matrix, which basically shows what the model confused with what showed very high accuracy for most species. Passer, the common sparrow, actually achieved a perfect 100% score.
Perfect for sparrows, okay.
But some species, specifically Tringotitanus and Himantopus, they both belong to the sandpiper genus, were more frequently misclassified as each other.
Ah, closely related species.
Exactly. This misclassification was attributed to their shared genus, resulting in very similar, often shorter song characteristics. It made it harder for the model to reliably differentiate between them.
So even advanced AI can struggle with close relatives if their songs are very alike.
It's a good reminder, yeah, there are still nuances.
And to ensure these impressive results aren't just, a fluke or specific to this one training run, how did they ensure its reliability?
Good question. They performed rigorous statistical analysis. A t-test showed that the 3.06% accuracy improvement from the baseline model was highly statistically significant p-value, less than 0.00001. So very unlikely to be random chance.
Okay, statistically sound.
And additionally, they employed five-fold cross-validation. That's a standard technique to evaluate how well the model generalizes and to mitigate overfitting.
Right, make sure it didn't just memorize the training data.
Yeah, precisely. The results from this cross-validation showed strong robustness. Accuracy only fluctuated minimally, a mean of 96.04%, with a very low standard deviation of 0.18%. This confirms the model's consistency and its ability to perform reliably.
This deep dive has truly unpacked some cutting-edge advancements in birdsong recognition. It's fascinating how a clever combination of these attention mechanisms, kernel adjustments, and optimization algorithms can create a model that's both highly accurate and incredibly lightweight.
Indeed. It's a fantastic example of specialized AI solving complex real-world problems.
Yeah.
This research offers a really significant step forward in enabling more convenient and effective birdsong monitoring in the field. And that capability is just a vital tool for conservation efforts, especially in a world where bird species diversity is, well, unfortunately, facing profound and increasing challenges. It lets us gather data on a scale previously unimaginable, giving crucial insights into ecosystem health.
So what does this all mean for you listening? Beyond direct conservation, just consider the potential for broader ecological research. Imagine a future where citizen science projects could really flourish, where anyone with a simple, inexpensive field device could contribute to vast, real-time data sets of global birdsong.
Crowdsourcing ecological data.
Exactly. This could provide immediate, granular insights into ecosystem health, biodiversity hotspots, even the subtle impacts of climate change or human activity across huge geographical areas. This kind of technological leap could truly empower a new era of environmental stewardship, putting powerful scientific tools into the hands of many, making everyone, really, a guardian of our planet's natural symphony.